outbreak detection and activity levels and different methodologies to try and think a little bit on how can we, starting from any given, so we have an epidemiological curve, so new cases over time, for instance. If we look at this trajectory, for instance, okay, so imagine that, suppose that this is new cases or incidents, sorry, over time, be it daily counts, weekly, monthly, or whatever. What we want to do is a way to be able to, in future events, identify when we have the starting of the process of increase of new cases, right? So sustained increase. You've seen in Roberto's talk yesterday, and a little bit with Renato as well, that one way, if we have a dynamical model, a compartmental model for our disease transmission process, this period here could be associated with the estimation of an exponential growth, right? So we can try to fit an exponential curve in some window here, and then estimate the parameter associated with that, and in some way try to establish whether we have sustained transmission or not. So, for instance, then if we have some noisy data, okay, here is more or less a simple process where we can fit an exponential and then see over time for each time step here what is the associated slope with the fitted exponential, and then define a threshold for this being sufficiently positive in order to associate that, well, at a given point in time we have the initial phase of the sustained transmission. This is one way to look at the problem, but then when we go into real data, usually we have some noisy time series. Of course, we could smooth it out. For instance, using rolling averages with any window that we manage. For instance, we can take the rolling mean of our observations over 3 time units, 4 time units, or whatever, and this is a way to smooth out the actual observed case and have something that is more suitable for a fitting process, right? For whatever function that we can come up with. But still, even smoothing it out, we can see that it is likely that we have some small periods of time where we already will have a positive rate for an exponential fit. But the question is, are those events already enough for me to establish that I'm already in the outbreak phase or not. Just with the slope, I cannot do that, right? Because in principle, we could have the slope here in those small outbreaks or small bursts, more or less the same as the initial phase of when we do have sustained increase. So how can we separate one thing from the other? Okay, so this is what we will be focusing on in this class of today. So the question is, well, what defines the period of epidemic outbreak or activity? When does it start? How long does it take? One way is trying to fit an exponential growth, look at whether the effective reproductive number at a given point is already above 1 or not. And another way to look at it is to try and establish activity thresholds directly, right? So instead of looking at whether the pattern is increasing, I will look at the actual number of reported cases at any given week and check whether that number of cases is compatible with fluctuation state or already with sustained increase. Of course, for that, I need historical data, long enough historical data to be able to separate and identify what is baseline and what is above baseline, okay? But the idea is that I'm moving away from looking at the slope and going forward into looking at actual number of new cases. This also has some practical aspects that, well, I no longer need to deal that much with the noisiness of the data, right? The inherent stochasticity of the data. I do not need to keep fitting my data to exponential functions all over the time, right? I don't have to deal also with the window that I will use to fit my exponential, and so on and so forth. Okay? I just, as long as I have historical data, once I define, I'm able to define those the threshold, I can on the oncoming season. Once I have crossed this threshold, I'd say, okay, so from now on, what I expect is to have increasing number of cases for several weeks before it's starting to go back down, right? So, how can we tackle that process? So, again, now, we can see here, again, we must, how can I be certain that those bursts, or how do I define that those previous bursts are still within my baseline, or is already large enough for me to trigger specific actions, right? So for instance, taking as an example, the notified cases of influenza H1N1 in 2009 here in Brazil, so during the 2009 pandemic. You can see that, so we have here in light gray the notified cases, and in black the confirmed cases. So the gray one is syndromic. The black one is related to those that actually had positive tests for influenza A, H1N1. And we can see that here we already had a bump. And then afterwards, there was this huge increase. So we had some sustained higher level of activity here if compared to what was previously going on. Then it decreased, and then it started again. Now, without knowing the operational details leading to this first burst, when would I say that the epidemic actually started in Brazil, based only on that figure? Around mid-June, mid-July, more or less, already here in mid-June. So we see that there is clearly a decrease here, right? So one might assume that this was something else going on, and the actual invasion process, established an invasion process, only started around here, more or less. So after July, right? Now the thing is that if this small burst here wasn't so close to the actual to the next phase, what happened in May, for instance, would that already be enough for us to classify it as a sustained outbreak that happened by some other respiratory infection, even for influenza, but not the pandemic strain already? It could be. Depends on what I used to have before that time, right? This is the central point. What was the expected volume of cases, right? Just by looking at what happened after that is not enough for me to classify what happened here. I can only say that, well, something different happened in those two periods of time, right? Now, in fact, what indeed happened here was a change in the notification process, in the protocols for notification of cases. Okay, so this goes back a little bit to the class of yesterday on the impact of the surveillance system itself in the data that we are looking at. Okay, but let's not dive too deep into that at the moment. So it's just to have this in mind. So as we were mentioning here in the beginning, now in terms of activity thresholds, we will adopt this paradigm change that instead of looking at the increase rate, we will look at incidence volume. Again, just by looking at the increase rate, we have more or less the beginning of those two phases here, more or less the same picture. What differs from one another is the volume of cases itself, right? The slope, the initial slope is more or less the same. Now, so we will try to establish an incidence level above which we can separate baseline and sustained increase. And this turning point, we will then call it either pre-epidemic threshold or epidemic threshold. There in the literature, you can find both terms as being used, depending a little bit on how the method is structured, but the application is exactly the same. So it's not really important whether we use it, we call it pre-epidemic or epidemic threshold. Now, again, how to estimate that? Again, we have a problem of sensitivity against specificity, right? Because I want to have a level a threshold that clearly identifies actual outbreaks, right? But we do not want for it to be triggered every time that I have a small burst. Okay, so I need something that it's able to correctly classify my outbreaks. But of course, this, if you see and look at this picture here, you can see that if I had defined my threshold at this point, okay, I would ignore or classify what happened here as still compatible with stochastic fluctuations, baseline activity. And here I would say that, well, now I have the starting phase of my increase. And then we might be questioned on site that, well, we triggered the initial alert response, and a little afterwards, the number of cases decreased below our epidemic threshold. Do we turn it off or not? All right, we can see that a little bit later, we crossed it again. Not only that, but also we could, just looking post facto to this time series, we could say that, well, at this point in time, I could already classify as the actual initial phase of my epidemic state, right? Because already from this point on, I have a steady increase of cases. So I delayed my actions in a few days or weeks, okay? But this was necessary for me to avoid triggering actions on those two phases here that were not already of relevance to my particular scenario, okay? So this is something that is strictly related to sensitivity and specificity. I will allow myself to be to start my actions later on, but having a stronger assurance that I'm not triggering false alarms, okay? And again, how we do that depends on the historical data. And the price that we pay also depends on the structure of my particular disease scenario. And we will see how we try to manage that. Okay, so, this is already discussed. So, the USA CDC uses for influenza-like illnesses a baseline that is that takes into account the previous seasons, and then it separates this process in two phases. So first of all, let me just draw a sequence of seasons here. Let's say that we have these time series here of as historical data. We divide our trajectory here in 3 seasons. Okay, it could be year-long or from mid-year to mid-year, depends on when we have concentrated activity. But the central idea is that I would try to separate in different seasons the activity peaks, okay? It doesn't matter much how long each of those seasons take. The important point is that I clearly separate the peaks, okay? So each season I try to accommodate in a way that my incidence over time is unimodal. It has only one clear peak and not 2 or 3 within the same season, okay? And then what we will do, or the proposal of the US CDC, is that I will try, first of all, I will look into, within each of those seasons, and I will separate non-influenza weeks with influenza weeks. So basically, try to identify what is baseline and what is not baseline, looking at the percentage of patient visits with respect at each given week, the number of cases, how it compares to the percentage of total cases over a season. Okay, so I have the total number of cases for each of those seasons. At each season, I will look at when the number of cases is above a certain percentage of the total number of cases within that season. Okay, with this step, of course, it can vary from season to season. I will say that whatever is below or before that time, that point in time, we will call baseline, or in their terminology, non-influenza weeks. Okay, and then we will look at the characteristics of what happened in that period of time to establish the actual epidemic threshold. So we have two separate phases. First is a gross approximation of when I have high enough number of new cases, and then separating, looking at what happened before that time at each season. I will look at the distribution of those cases to then define my activity level. So, first point, non-influenza time period defined as 2 or more consecutive weeks in which each week accounted for less than 2% of the season total number of specimens that tested positive for influenza in public health laboratories. So in my Sentinel surveillance system, okay? Here they are using positive cases, but it's not necessary for it to be positive cases, okay? Whatever data I have that I want to establish epidemic threshold, as long, again, as we discussed yesterday, as long as my data is homogeneous in time in terms of what is actually being accounted for or notified, is good to go. Okay, I could use syndromic surveillance right away. Okay, of course, the price that I will pay is that at different periods in time, I might have different viruses being associated to what is going on. But this is a price to pay for a surveillance and activity threshold for ILI in general, and not for influenza specifically, or for RSV in particular, or for COVID, or for adenovirus, or whatever. Okay, the same things for arbovirus surveillance, right? That it can take into account the the aggregate number of suspect cases of dengue and chikungunya, throw it in the same basket and do the same thing, or separate that data set and on specific positive dengue cases, positive chikungunya, and so on and so forth. Okay? As long as I'm looking at the same data all the time, this should be enough. Okay? So, what we have to do in practice then is for each season, calculate the total number of cases at that season. From that point, I look at what is the 2% of that total, and so I will establish a first approximation of an epidemic threshold that is based only on that. And with that, I can then separate my time series on non-epidemic activity and epidemic activity, okay, based on that first approximation. Right, so my first approximation is just that. From the epidemic threshold, the first approximation for the epidemic threshold is 2% of the total number of cases on a specific season. So for each season, I will have, in principle, a different threshold. So for this is a picture of notified influenza cases in Germany in 1918. And if I'm not mistaken, the time unit here is days. And with that first approach, what we will have as an epidemic threshold will be over here. We can see from that picture that is still quite high, right? It's extremely high. If I take the this phase here as my expected baseline, we can see that the threshold established here is way, way, way above my season activity, usual activity, right? But remember, this is just the first step of the approach proposed by the CDC. What we do then is, well, now I look at the distribution for the 3 previous seasons that I have. I aggregate all of the cases that are outside, that are below this threshold, that I will classify as non-influenza weeks, and I will look at the distribution of those cases, okay? So I first do a gross separation between non-epidemic and epidemic, and then I draw the distribution of weekly counts or daily counts or whatever for all the weeks or days where I am below that first threshold. And with that distribution in mind, then I look at the mean of this distribution and 2 standard deviations from the mean. And this will be then my actual activity threshold, my epidemic threshold. Okay, so I'm taking this gross approximation just to have a distribution of expected cases below a certain activity threshold, okay? And with that, I will see, well, for those cases, where are the outliers? And the outlier then I will use as the epidemic threshold. Okay? So of course, now you can see that if my first step would already put this barrier too low, my outliers would be too close to the actual fluctuation that I have at baseline. And this could lead to false alerts, to false alarms. Okay? So this is why my first step is a gross approximation far away from what I actually want to establish as the epidemic threshold. Okay? The idea is just to have a large enough distribution of cases outside the peak and look at the distribution of that and to establish what is the aberrant or outlier observations. So again, using the same example, the epidemic threshold itself, based on the CDC approach, would be here more or less at 100 something, 115, 20 more or less, 120 I think it was. So you can see that we already lowered quite well from the first approximation. Okay? Yeah, sure. Sure. So the idea is that I look at the distribution of all the observations of what I classified as non-influenza weeks or non-outbreak weeks. I look at the distribution of those observations and I calculate the mean plus 2 standard deviations. And the result of that calculation will be my epidemic threshold. Is that clear? Okay. Of course, we could argue that, well, standard deviation doesn't make much sense for this particular distribution of observations. I could use directly quantiles to establish what is already an outlier on that distribution, instead of looking at mean plus standard deviation, right? But the central point is that I first we will construct the distribution of cases that allows me to identify outliers at my baseline. Now, it looks right that for this particular example, Germany 1918, the threshold was quite high, but with the same, exactly the same approach, if we look at the data for the same disease, so flu cases, and Castilla and León in Spain 2000, on the season of 2001, 2002, we can see that the same approach is able to establish a threshold that is extremely accurate for that particular data set. So we have an issue of the underlying data, right? It's exactly the same model, but the outcome, the quality of the outcome is completely different. The only thing that changed was the underlying data, not the method. So this example is here just to show that, unfortunately, so far, there is not a golden standard for that. Okay, there is not a one-size-fits-all methodology. Of course, I could play, and I should play, with, for instance, both the what I use to define an outlier, right? Or also what I use to define this first step, this first gross separation between non-epidemic and epidemic activity, right? So with this approach alone, there's already two aspects that I might tweak in order to play with what we were discussing in the beginning, sensitivity and specificity of my method, okay? And there's no way around, no other way around. You have to play with your data. You have to look at your historical data and tweak the parameters of the method to see what is the best tuning of those parameters for your desired specificity and sensitivity, okay? And will not only change from disease to disease, but as the example here shows, it is very likely to change from place to place with the exact same disease, okay? So it's disease-specific and space-specific, okay, or population-specific, okay? Is that clear so far? Good? Another important point, of course, here we are just looking at one single season, right? The more seasons that we have, in principle, the better my estimation will be. Okay, because I will then have more observations for my more out of season or out of outbreak activity. So the quality of this distribution will likely get better, right? The more points I have. And so it might be better suited as the number of seasons that I use increases. Now, there's another method that is being widely used and used by the European CDC. The US CDC is also using some aspects of this method for some diseases as well, which is the moving epidemics method, or MEM. Okay, there's an R package associated with that, available on GitHub. And the logic behind the approach implemented on the moving epidemic method is exactly the same. Okay, I will first try to build a gross approximation of what is pre-epidemic activity, epidemic activity, and post-epidemic activity. And once I do that, I will again draw the distribution of observations on the what I defined as pre-epidemic period at each of the observed seasons, and then from that try to establish what is the outlier. Okay? The idea, the logic behind is exactly the same. What will change is how we go by performing this first step characterization or separation of my season into 3 categories, and how we deal with the distribution of observations of what I will call as a first approximation, what is my baseline. Okay, I have some articles here associated with the method that goes into a little bit of the details behind the machinery, but the actual package is quite good to dwell also as a reference. So the starting point of the MEM approach is based on what they call the MAP curve, which is the maximum accumulated percentage curve. So again, we are taking into account the total number of cases at each season, just like the CDC approach used. Okay, but instead of predefining a percentage of my total cases, total season cases, I will look at when I have the larger number of accumulated cases. So I'll play with windows inside each season to look where I have a higher concentration of cases on a short period of time. So I have to play with window size and volume, accumulated volume within that window size. Okay? Of course, the larger the window, the larger the accumulated number of cases. So I have to somehow minimize the window size while maximizing the accumulated number of cases, right? So, what is the map curve? It's just a function of window size, okay, that looks at what is the maximum accumulated number of cases for each window size, possible window size within any given season. So for each season, I will build a specific map curve, okay, that is playing. Let me take here an example of how this process goes on. So I have here a season of size S in terms of time units, okay, or observations that I have. Let's say 52 weeks, for instance, if I'm looking at a full year with weekly cases, right? I have usually 52 weeks in a given year. So I can play then with windows of size 1, which would just be the weekly counts, right? And so for as a window size of 1, what will be the map curve, the value of the map curve for a window of size 1, where it will be, first of all? Sorry? 1? So, what I do is, for each window of size R, I calculate the accumulated number of cases with that much consecutive time steps, okay? So of time 1, I will look at week 1, week 2, 3, 4, 5, each of those separately, right? Because my window is of size 1. And then the map curve is the ratio between the max of that process over the total number of cases within the season. Okay? My first question is, where will it be? Okay, because for each window size, I will look at what is the highest possible value observed. And of course, for that value, there will be a specific place of that window, right? Because I will be moving that window over my time series. And once I find where do I have this maximum, that will be the value of the map curve and also where it happens, okay? So in terms of the actual value of the map curve at R equals 1, it varies. It's hard to assess. But when it happens, should be quite clear, based on the idea behind this curve, right? Because what is the maximum value? Where is the maximum value? At the peak, right? Because for window size 1, I'm looking at every single observation. So the maximum value will be the peak at that season. So in terms of when it happened, I know it's here. Okay? Which is the I over there within my maxima there for in the definition of C of R. Okay? Is it clear, the notation there? Does anyone have a difficulty understanding what is? Sure, go ahead. Yeah. So I is the starting point. Okay? So for a window of size 1, I can start at week 1, week 2, week 3, week 4, whatever, and I will, since the size is just 1, I will only look at that specific value. For a window of size 3, let's say, I will have first from 1 to 3, then from 2 to 4, 3 to 5, and so on and so forth, right? So I have this moving window. And what C is doing right there, C of R, is to check where this window is maximum, corresponds to a maximum. So with this logic in mind, for R equals 1, it must be the peak for that given season, right? Clear enough. Now, the value, of course, will depend on not only the amplitude, so the actual number of cases observed at the peak, but also how the cases are distributed along the other weeks, the other observations, right? Because it's the percentage of observed accumulated cases with respect to the total cases over the season, right? So the actual value of the map curve at 1 might vary depending on the shape of the curve itself for each season. But when it happens, there's no other way around. It must be at the peak of that season, at every given season. Now, the same process we do for window sizes from 1 all the way up to the total number of observations that I have on a given season. So the final value for the map curve P of R, where R is maximum, so R equal to the total number of observations, it must be 1. Right? Now, with that idea in mind, looking at the definition and the construction of that particular function, can I already have information on what is the behavior of that curve? Is it something that increases, decreases, or oscillates? Is it a function that is non-decreasing, non-increasing? What can I say about it? Is it possible to make already an assessment of this type of characteristic for that function? Based on simply on the definition of it. Again, is for each value of R is the percentage of accumulated cases over the total number of all observed cases. So it's the maximum over for that particular window size over the total counts. So for a window of size 1, and I'm always looking at the maximum, right? For window size 1, I take the maximum. For window of size 2, I take the maximum, and so on, so on, so on, and so forth. So the value for R equals 1 and R equals 2, is it possible to infer whether this curve would stay the same, will go down or go up? It must increase. It must increase. Unless I have only one point in my whole series. Then it will be constant, right? So at least it is a non-decreasing function, right? Because it should increase, but at some point it might stabilize itself, right? Because I might have weeks that have no activity whatsoever. So let's say if I have 1 week without any observation, then window sizes of, let's say that I have 52 weeks, 52 observations. The value for P equals 51 and P equals 52 must be the same, right? Because the only additional point that I'm introducing from going to window 51 to window 52 will be 0, okay? So there will be a certain point where I might have a stability of this function, okay? But it cannot decrease. It will not decrease. At most, it will remain a constant, okay? So we will have then, so from this, from a given season, I will construct my map function P of R that I expect to be something like this, more or less. Right? It should look something like that. Of course, in the beginning, any small change in window size might lead to a strong increase in my percentage of accumulated cases, but as my window sizes get bigger and bigger, the difference from adding 1 or 2 weeks to my window size shouldn't matter that much, right? If my season looks like this. Otherwise, I might have something completely different. If over a season the cases are only increasing, this will be something different whatsoever. So we are already assuming that any given season behaves something like that. Okay, I will have an increasing phase, and then I will have a decreasing phase. Okay, otherwise, the whole concept it's out of the window. So for the 2 examples that we've seen so far, the associated map curve for those 2 seasons are depicted here. So for Germany, we have daily counts. For flu in Castilla and León, we have weekly counts, and both of them, in terms of the shape of the curve, looks more or less the same. And it should be. They should look more or less the same. Okay, because it's just a basic consequence of the structure of the data that we expect to be using and the definition of the map curve itself. Now the question is, well, okay, great. I have this, what I do about it? So we want, based on this curve, to be able to assess, well, when do I start to, now I'm changing the threshold over the curve that I had to defining a threshold to this other function, right? I want to be able to identify here, when do I have a clear changing pattern? When do I change from this strong or rapid increase in the accumulated number of cases as a function of the window size? Because when it starts to bend, this means that now I moved from something that looked like this to something that went from here to here, or from here to here. right? Because then when once I start to increase my window size, I'm aggregating more and more weeks that are closer and closer to the baseline, be it before the peak, the observed peak, or after the observed peak, right? So is it clear for everyone, right? For for window size 1, we have the peak. For window size 2, we will have something that is around the peak. Window size 3, we will add 1 week to the left or to the right, and so on and so forth. So we are basically stretching the window here and leaving it to the function to define whether I move into the left or to the right as I add one additional observation, right? So at some point, adding 1 week, 1 or 2 weeks, I'm including more and more observations that are close to the baseline, and so the contribution to the map curve will get lower and lower. And so what I want to do with this curve is to be able to define with this curve that is much more smooth than the original data set, be able to, when I transition from windows that are around the peak to windows that are including baseline observations, okay? So one way to do that would be to simply look at the derivative of this curve, right? Because here I have a very high slope, and as I move my window size, the derivative gets lower and lower and closer to 0. So I could, for instance, let's say, establish an a priori threshold to my derivative, right? So instead of putting a threshold in the map curve itself, I put a threshold on the derivative of this curve. And I will have, out of that, so if let's say that I put a value that is, say, corresponding to an angle of 45 degrees, for instance. Okay, depending on the shape of this curve, it will be, the window size will be higher or lower, but this will give me the duration of the peak, the duration of the highest accumulated cases, and with that, I move back to the construction of the map curve, and I look at, well, for this window size, where is it located? And from that, I have a tau, which is associated with what I will call as the initial phase of my high activity period. So more or less the same way that for the CDC we had the 2% of the total counts, I have here when in time I'm separating baseline and higher activity. Okay, this would be the equivalent of our non-influenza week on the CDC approach. Okay, so we are not looking at the cases directly, but when I have a higher accumulated number of cases. Okay, so the starting point, the logic and the starting point was the same, but the approach that we are taking is already completely different. Right? Here it's looking at single points, single observations that crosses a threshold over the total counts. Here I'm looking at accumulated, when I have a higher accumulated number of cases. Okay? So by this approach, I only get a starting point. With that, I already have starting and ending point. So I can define pre-epidemic phase and post-epidemic phase, right? And the characteristics of those two might be different. And in fact, they usually are. We have a rapid increase and a slow decrease, usually. Right? We've seen this on the previous lectures as well. Right? This is usually what we have in our models, and this is, in fact, what usually we see in the data itself. So separating the two, again, might be interesting. Why? Because let's go back to the Germany example, for instance. So we see that here in Germany, we have several points here that are way above what we could just by empirically attribute as baseline, right? Both the periods before and after this line here, so as long as the observed cases are below this threshold, we are including in non-influenza weeks, so in the baseline that we use for calculating the distribution, right? So I'm including several observations that are much higher than my baseline. Most of them are coming from after the peak, not from before the peak. Before the peak, I will have usually just a few observations that are above baseline. So using this distribution instead of the overall distribution might lead to a better definition of the epidemic threshold, even with the CDC method, the CDC approach of looking at the distribution of non-outbreak weeks, okay? And here, with the MEM method, they are already exploiting that particularity. Because now, what we will do is that we will look only at the distribution of the pre-epidemic phase observations and not use the post-epidemic ones. Okay? The post-epidemic ones we can use to define a post-epidemic threshold. Right? So to when I can relax. Those might be different. Those usually will be different. Okay? And I can only do that if I separate those two. Okay? So now, the real question, how do we exploit this curve to try to have a better assessment of this first step of separating pre-epidemic, epidemic, and post-epidemic phase on every single season. So for each season, I run the same process. So one approach, so and this is one good thing also on the R package provided in the GitHub, is that you have different methods, right, to apply over the math curve to establish this characterization of pre-epidemic, epidemic, and post-epidemic threshold. And you can play with different methods to see what fits best to your data set. Okay, it's not already hard-coded on one single approach. So we will see here some examples. Okay, so the first method proposed there, it proposes a change of variables here over the map curve to try to, so we will try to minimize this function here where R hat is just the normalized window size. Okay, so R is the window size. I'm redefining R here based on the minimum and maximum window sizes that I have on my data set. Okay, so that it scales from 0 to 1. Okay, so that it doesn't matter if a given week is, if a given season has 30 weeks or 52 weeks, the range of R will be the same. It will go from 0 to 1, okay? Once I do that change of variables, that normalization process, right? Now, because again, remember, we want to do the same approach for different Cs and an aggregate. And I will look also at the variation of the map curve, basically a rough approximation of the derivative of the curve, assuming that I have, and usually I will have, discrete observations, right? Because my original data is discrete over time. So map will also be discrete over time because the window sizes, they are not continuous. They are always discrete, right? Be it days, be it weeks, be it wherever. They are discrete in nature. So I will look at not actually the derivative, but the point difference of the map curve. And also, and again, I will normalize this difference, this point difference, okay? So that again, so that both the normalized window size varies from 0 to 1, and the normalized difference of my map curve, it's also normalized from 0 to 1, okay? Now, R is an increasing function, right? It's window size. Window size will only increase, right? Now, what about this difference here? Remember, the map curve looks like this. What can I say about the derivative of this function? Whoop. So, let's see. For R equals, when R is small, I have a very high derivative, right? A very high slope. Once I move forward on window sizes, this curve is decreasing, is reaching an asymptote, so the derivative is getting closer and closer to 0. So it's diminishing, right? So it's a non-increasing function. The map curve is a non-decreasing function, and the derivative associated with that is a non-increasing function. Usually it will be a decreasing function, but at least non-increasing for sure. Okay? So it will look something like this, let's say. Okay? So, if I minimize a function that is a mixture of R and the variation of the map curve, on the one hand, as R increases, R hat increases, but the difference in map curve decreases. So by minimizing this function here, I'm balancing between and trying to find the smallest window size with the highest accumulated case counts. Okay? Or the smallest window size with a big enough difference of map curve. So I'm trying to assess this inflection point without actually going into the second derivative of this function. Okay, I'm playing with the characteristic between window size and variance. And this is what we get. Okay, so, and remember, this is just the first step of the method, just to separate pre-epidemic, epidemic, and post-epidemic phase. Okay, so this is what we would get for the Germany one and for the Castilla-Leon example. So we can see that with that method, in both examples, we have a pretty good approximation already. And it's still not the epidemic threshold itself. What I will do now is, again, the same thing that the CDC proposes. I will look at the distribution of observations here for every season that I have of historical data and look at outliers on that distribution. Okay, so that the actual epidemic threshold will not be over here, but will be somewhere around here. And it will depend on how I define what is an outlier for those observations right there. Okay? And again, how do I go by defining outliers here? There is a huge variety of methods that I might use. I will not go over one by one because it's not fundamental. The point is that, well, I have a distribution that is built by this process, and what I will do is somehow try to define outliers over that distribution, okay? Be it on a parametric way, be it on a non-parametric way, okay, assuming that the distribution of those observations is Gaussian, is Poisson, is whatever, okay? So there's a huge window of possibilities there. Again, you have to plug and play to see what fits best. You could also run an analysis over the distribution to see if it has any particular shape, particular shape, right? If it looks like a geometric distribution, a Gaussian distribution, or wherever, and then use the properties associated with that particular distribution. Or I can ignore that completely and go to a non-parametric approach and just look at quantiles and be done with it. Okay? Is that clear? Is it okay? Right. So another possibility within the MEM approach is what we discussed in the beginning. I will just establish a threshold for the unit difference of the map curve, and I'll look at what is the smallest window size with a slope that is below that particular threshold. Okay, remember, the slope is always decreasing. So when I define a threshold, based on an upper limit for my slope, I'm moving to the left in window size, right? Because as I lower my window size, I increase my slope. Based on empirical observations, they propose the usage of values between 2 and 4 for that as threshold for the difference. Okay, again, this threshold only makes sense because of how we define the map curve. And we see that, I think here the threshold was 2 point, I don't remember if it's 2.3 or 2.8. But you can see that already we have here for the Germany example, a window that is much lower than what we had before, right? And also the starting point is different. But for the Castilla-León example, we have pretty much the same thing. The starting point is exactly the same. The only difference is that for the first method, we went 1 week ahead in comparison with the difference, the threshold in the map curve difference approach. It's pretty much the same thing. Again, this is to show that the underlying data affects also how the different methods differ from one another. Okay, here we have a clear example of 2 curves that for one, both methods give pretty much the exact same result, and another one where they differ drastically. Right? And then even if we use the same approach for defining outlier in the distribution of the pre-epidemic cases, I would have a completely different outcome for the German example, but the same thing for the Castilla y León. Okay? Just because I change how I use the map curve to define what is pre-epidemic and epidemic periods. Finally, we could think about just throwing away this whole idea of the map curve and just look at the inflection point in my case distribution time series and be done with it. Right? Because remember, what is the idea behind the inflection point? Is exactly this change when I am in an increasing phase and suddenly I start to change the concavity of my curve. So I'm reaching the peak of infection. So I could use the inflection point, would be something, let's say, around here, more or less, in this example. Right? The logic is pretty much the same. I'm changing the method again, but the logic behind is exactly the same. Okay? Now, from the strictly mathematical point of view, makes a lot of sense, but when you look at the underlying data, we can see several possible drawbacks. First of all, we might have inflection points within my baseline. Okay, I could throw those out by smoothing out this curve, be some approach. Okay, or look on how spaced they are from one another to discard the first ones and keep one that makes sense. I could build an heuristic approach for that, but also the fact that we might also have extremely noisy data, not only the fact that we might have small outbursts beforehand, the fact that even when I am in my increasing phase, I might have noise around that process. This could affect my inflection point estimation. Okay? But in principle, I could use and would lead more or less on the same idea behind definition of an epidemic threshold. Okay, and this is just an example again on those two curves. We can see that for Germany now we are more or less close to what we had with method 1 based on the map curve. Okay, it's a little bit lower, and for the Castilla example, we're still more or less at the same level, the same point. Okay, and also another interesting thing that in terms of inflection point, we could, same way as here, identify not only the starting point but also the ending point of this high activity period, right? Just looking at whether the sign change that I'm looking at based on the inflection point. Now, everything nice and dandy, but then we have, again, the problem of real data, pesky real data. So here is an example out of study case notification in the state of Rondônia, here in Brazil, from 2010 all the way to 2016. And here, zooming out on 2011 alone, there's nothing to be done with this with this particular season. There's no way to define what is pre-epidemic or epidemic state here, right? So more or less the same. Okay, that for this particular example, it's just one observations at each time point, but it could, even if it was fluctuating about 2 to 3 it will be more or less the same thing. I will have extreme difficulty in defining what is epidemic and pre-epidemic. Right? The map curve would most likely say that this region here would be my epidemic phase. But if the cases were more dispersed over time without a clear accumulation, I might have the whole season as my epidemic phase. And what do I do then? Okay. So one approach, one possible way to tackle that is, while looking at the historical data, define a threshold to discard seasons with low activity and keep only those that have a clear peak, for instance. So I throw away all the seasons that are just fluctuation and keep only the ones that have a clear peak. And over that, I apply whatever method that I want. Okay? This is something that should be done. Okay? And the only way to assess that is looking at your data set. Okay? The data will tell you whether this approach is needed or not. Okay? And you can also build a recurring approach where you go over your proposed approach over all the seasons. You define an epidemic threshold over that, and you use that first passage to discard seasons that are, for the whole season, below that threshold that you calculated over the full set of seasons that you used. Okay, so you do a first run to discard seasons that are significantly below your usual pattern, and then you rerun your approach on the remaining season. Okay, this can be done programmatically. With that type of approach, you don't need to look at the data directly. You can program it to do it for you. Because you run the whole method, you will get an activity threshold. If it makes sense or not, doesn't matter. Any of those approaches will give you an epidemic threshold. It will be up to you to confront that threshold with your historical data to check whether it makes sense or not, as we've just seen in the examples right here. Okay? But you can programmatically implement your model to run this first passage, discard seasons that all the observations are below what have come out on the first passage, and then run it again to recalculate or recalibrate. Okay? And another important point here. So, and then we end for today. Remember, we only went over the definition or estimation of epidemic threshold, or pre-epidemic threshold if you want. But we've seen already that on the first approach, on any method that we discussed so far, on the first pass, we already get rough approximations or rough classifications of pre-epidemic, epidemic, and post-epidemic phase for each season, right? And we used the distribution of cases on the pre-epidemic phase to define what is our epidemic threshold, okay? But as we discussed, we can do the same thing with this chunk over here to define post-epidemic threshold, and we can also look at this chunk over here to classify the peaks of each season, whether the observed peak in a given season is significantly different from what I have in general, right? Because again, I have a distribution of observations here. So I can again look at outliers here to classify my seasons in terms of the peak of activity. Was it within what is expected? How would I define expected? By looking at the median, for instance, of this distribution, right? This will give me what is the expected peak at any given season. Now, if I look at the percentile 90, let's say, I will be able to define what is significantly higher peak based on my historical data. I can look at lower percentiles to classify low activity or low peak seasons, right? I have this whole universe of points here to apply at the end, on the final step, pretty much the same analysis. Outliers for the distribution of observed cases at each of those particular regions. Okay? Last but not least, this idea of building distributions and calculating thresholds for the distribution, we could also apply for every single week. So if I have, let's say, 5 seasons, I can build a distribution of all the observations at week 1, all the observations at week 2, all the observations at week 3, and so on and so forth. And then, by looking at the distribution for every specific weeks, I can provide an approximation to what is the expected number of cases at every single week, which is what we call usually the endemic channels in epidemiology, right? Which is a curve that gives us exactly that. What is the expected number of cases along a given season? It's not a threshold anymore, right? Because the thresholds that we've discussed so far is the same value no matter when it happens. As long as the number of observed cases is above that value, it doesn't matter if it's at week 1, at week 15, week 30. If it crosses that value, with the method that we discussed here, we have a strong likelihood that we are starting our outbreak, right? Or our steady increase phase. By building that process for every single week, I'm kind of defining thresholds for every single week. Of course, around here, if all the seasons have more or less the same structure over time, which is to say that the peak is more or less around the same period of the year, now the expected number of cases around here will be high. The expected number of cases over here would be low. So it's not an epidemic threshold anymore, right? Because to be above what is expected over here does not necessarily means that I'm already at my steady increase phase. It might just mean that, well, for some reason, the number of cases is still at baseline are already higher than what I expect. Okay? This is already something. It might not already necessarily lead to an intervention, right? But it's already indicative that, well, this season might be different from the usual. Because even now that cases are still at baseline, the baseline is already above what I usually observe. Okay? This might lead to an early start of the epidemic phase, for instance. This might lead to a higher peak. Okay? So it's already actionable information, although the type of action that I implement will be different. Okay? Any questions? Lots of questions. questions. But, well, is the idea clear so far? Okay? Now, with the MEM method, they also have this approach to calculate endemic channels. And also, another thing that is quite interesting here is that, well, since we have this rough approximation of the starting point of my epidemic phase for every different season, what I can do as well is then, well, if I have one season that looked like that, and then I have another one that was early on, let's say, so my method said that the epidemic phase started here, and then I have another one that was a little bit later, so it started here. Now, if I pile up all those curves, as we were discussing in terms of endemic channels, the fact that for this season the peak was earlier, it will throw the expected number of cases over this period of time upwards, right? Even though for the other two seasons, it was still at more or less baseline. Okay? What the MEM methods proposes, and is the reason why it's called moving epidemic method, is that, well, if I want to understand what is the shape of the curve once the outbreak starts, I can shift each of those seasons so that the starting of the epidemic phase coincides for all of them. And once they are aligned, then I calculate the expected number of cases for every single week. Okay? So this will give me a snapshot of what I expect in terms of the pattern of the curve. But when will it happen? I don't know, because it varies. But I also have information. Well, I can also calculate the distribution of those point in times to try to estimate, well, when is the most likely period of the year to observe the starting of the epidemic phase. Okay? And I can use that as well. Okay, so there are lots of information that can be drawn out by this approach. Questions? The quality of the threshold by plugging it on top of your historical data. Simple as that. So it's basically empirical in nature. So in fact, what have been done by the European CDC when they started using this approach is that they gathered a pool of experts to evaluate the outcome and then define what was the best tuning parameters for influenza. Okay? And this is it. This is it. You look at it and then you're fine. Of course, you might try to construct methods to calculate what is the distance between what we had and the epidemic threshold, but this is basically the distribution that you use to construct the epidemic threshold. So you're not getting any additional information. Okay? So this is an open question still. How to programmatically or methodologically do that analysis. So far, it's empirical in nature. You look at it and then you decide. Lunch? Lunch. Thank you. Diga.